Hello, everyone. Before describing the data in our statistical sample, we want to talk a little bit first about the types of variables that we might collect. We're going to talk about two different kinds of categorical variables, nominal and ordinal data, and two types of numerical data, discrete and continuous. But before we talk about those, let's first go over what a variable is. A variable is just any characteristic or measurement that differs among individuals or other sampling units. So these are the things that we're measuring either as a response variable or maybe a predictor variable in our statistical sample. For example, you might collect a statistical sample of 22 gray jays in Algonquin Park. And for each of those jays, you might measure the bird's age. Alternatively, you might measure the chlorophyll A concentration in 45 different lakes, or the carbon content in 22 peat cores, or maybe the preference for antler points from 112 white-tailed deer hunters. In these cases, age, chlorophyll A concentration, carbon content, and antler preference are all examples of variables. There are two main classes of variables that we're interested in: categorical variables and numerical variables. Categorical variables are classified. Each observation is classified into a particular category, whereas with a numerical variable, we're actually measuring something about that entity. So for categorical variables, we're interested in classifying observations into two or more categories. So for example, we might classify individuals as being alive or dead, or belonging to one of 4 life stages, or perhaps identifying which species an individual belongs to. We can further subdivide categorical variables into either nominal or ordinal variables. For nominal variables, the levels of our categories don't follow any logical order. So for example, different colors don't fall in any logical order, or the identity of a species doesn't fall in any logical order. In contrast, ordinal variables do have a logical order. For example, egg, larva, juvenile, and adult follows an ontogenetic progression, or class size, classified as either small, medium, or large, follows a logical order. That is, medium logically falls between small and large. If you're having trouble remembering the definitions of nominal and ordinal, you can always try and remember that nom en français is name, and ordinal is similar to the word order. So in ordinal variables, the categories follow a logical order. One last note between nominal and ordinal data: anytime we have only two levels in our categorical variable, by definition, that variable is defined to be nominal. In contrast to categorical variables, numerical variables involve actually measuring an amount of something. So we might, instead of categorizing, measure the body mass, leg length, chlorophyll concentration, clutch size, or number of flowers. These variables aren't categorized, instead they're measured. We also have two different types of numeric variables then: continuous numeric variables and discrete numeric variables. Continuous numeric variables like body size can take on any real number, and there's no limit to the closeness of any two measurements. Whereas with discrete numeric variables, we can list the possible values. There are gaps between these possible values for which we can't have any values. In most cases, discrete numeric variables are things that we count. So for example, a continuous numeric variable might be body mass or leg length or percent body fat, whereas discrete numeric variables might be things like clutch size or the number of flowers, or the age at which an individual dies as measured in years. There are some important properties of these variable types that are worth talking about. The first is that there is a logical order to the amount of information that's contained in each variable type. Nominal variables contain information only about the class of an observation, whereas ordinal data include both the class and the rank. Discrete numeric variables also include information about magnitude, but not precision. So variables with more information then could possibly be converted in retrospect to a variable type that contains less information, but we can't go in the opposite direction. So for example, if we measured leg length as a continuous variable, scoring it or measuring it as values such as 1.3 millimeters or 3.1 millimeters, we could later on round those values into discrete values in whole units of millimeters of 1, 2, 3, or 5. And we might further summarize these as being either small, medium, or large. And finally, if we wanted to categorize these in only a very gross scale, we might break this down or summarize it even further into categories of only small or large. And so we can take our continuous numeric variables and convert them into discrete, ordinal, or nominal types, but we can't go the other way around. If we had simply measured leg length as either being small or large, there would be no way to convert that nominal variable into a continuous numeric variable. And as a result, it's always best to try and collect your data in a variable type that contains more information, because it can always be summarized into a more general category later, but you can't go the other way around. So two important final thoughts about data types. The first is to recognize that sometimes we might choose to use a numeric scale to represent ordinal data. So in our data file, we might classify individuals that are at the egg stage with the number 1 instead of writing out the word egg. But that doesn't mean that this is a numeric variable. Categories that those numbers correspond to represent groups that organisms were classified into rather than counts. The second important point to make is that there's an important distinction between discrete numeric variables and ordinal variables. We might decide to classify age into decades as being between 0 and 9, 10 to 19, 30 to 39, 40 to 49, etc. And this would be a discrete numeric variable measured in units of decades. But if we took two of those decades and lumped them together into a new category, we would no longer have a discrete numeric variable. Instead, we would have an ordinal variable. Now we've got 5 categories of age, but they don't correspond to a discrete numeric variable. And the reason for this is because although the categories fall in a logical order, the interval between adjacent categories is not consistent. We have some categories that correspond to decades and some categories that correspond to 20-year intervals. And as a result, then, we no longer have a fundamental characteristic of a discrete numeric variable, which is that the interval between adjacent levels always remains consistent. And we can apply this same logic to our discussion earlier about the ordinal variable of life stage not being a numeric variable. The difference between egg and larva isn't necessarily the same as the difference between larva and juvenile or juvenile and adult. And so although the life stages fall in a logical order, the difference between successive life stages doesn't necessarily follow a consistent logical pattern. So this, I hope, helps to exemplify some of the differences then between a discrete numeric variable and an ordinal variable, which can sometimes be a little bit confusing. So in summary then, we talked about two general classes of variables, categorical and numerical. Within categorical variables, we talked about nominal data and ordinal data. Remember, ordinal data follow a logical order. In contrast, when talking about numerical data, we referred to two different variable types, discrete variables that are typically counted and continuous variables that can take on any real value.